So let's take a look at problem number 6, which deals with a roller coaster. So imagine you start here and you go slowly, slowly, slowly up to the top of the hill, then you're let go and you're rushed down here, and A is the bottom of this valley, and then you go up to the top of this hill, point B, and hopefully you've all had this sensation of riding a roller coaster. If you haven't, that's okay. I'll be honest, I'll confess that my first roller coaster was when I was a freshman in college. It happened to be Batman the Ride at Six Flags, and to this day it's still one of my favorite roller coasters. But I didn't, I guess, have the normal experience of having riding a roller coaster when I was younger, but hopefully you have. If not, just think about some sort of thrill ride, or maybe taking a ride in a car over hills and down into valleys. Okay, so pause the video, and I want you to fill in the chart there for the first column, the direction you feel you're pushed or pulled. Okay, so if you had this experience again, you start at the top of the hill here and you're going real slow, then you go faster and faster and faster, then we go to the bottom of the valley, letter A. How do you feel like you're being pushed? You should have that sensation of being sort of squished down into your seat, or maybe it happens like right before, right after you start to go up here, and so you feel like you're being pushed down. That's the direction you feel you're pushed, right? And then when you go up to the top of the hill, you slow down a little bit, but as you go over this hill really, really fast, you feel like you're being lifted up out of your seat, right? And so that sensation is being lifted up. But now let's take this from the perspective of circular motion, right? At point A, we're going in a curved path, and you can sort of imagine you're in part of like a really big circle, and we know in circular motion, the direction of the net force has to point towards the center, and the center of the circle is above you, which means the actual direction of the net force has to be up, right? And then letter B, if you imagine this as being part of a circle as well, you can almost like imagine a circular path here. Well, the center of the circle is down below us, and the net force has to point to the center, and so the actual direction of the net force is down. And so we have this, incongruity about how you feel versus what's actually happening. So let's talk about the difference between reality and illusion. The reality of the situation is what we've been dealing with here, right? That when we did the net force at the top of a hill, the net force has to point down. This makes sense. The weight is larger than the normal force. And at the bottom of a valley, I know it's a Ferris wheel, but the same general idea as going on a roller coaster. At the bottom of the valley, your net force has to point up, normal force has to be larger than weight. That's the reality of the situation, right? And so the reality is centripetal force. And I know we have a definition for this already in our notes, but it would be a good idea to add to it or write it again. We're just going to add some more details to it, right? Centripetal force is real. That's the very real net force pointing to the center, pulling the object into its circular path. In circular motion, the acceleration has to be towards the center, and the net force has to be towards the center, and that's what we call centripetal force, right? Centripetal means pointing to the center. This is reality. This is what actually happens. But that's not what you feel. What you feel is, in fact, the exact reverse of this. You might recall, back when we were talking about elevators moving up and down, accelerating up and down, that I mentioned this idea that humans are kind of wired backwards. We always feel accelerations in reverse. So when you're actually accelerating up, you feel like you're accelerating down. When you're actually accelerating down, you feel like you're accelerating up, because humans are very, very self-centered. We think everything's happening around us and to us. And so the illusion of this is this idea of centrifugal force, a phrase you've probably heard of before. In fact, when I first mentioned centripetal force, if you're thinking, that sounds like something I've heard before, but it's a little bit different, right? Centrifugal force is actually a phrase that's a little more popular. The problem with it, like I said here, is that it is illusion. It's not real. Centrifugal force is the fake force you think you feel, forcing you out of the circle. And of course, the real problem is that most people have heard of this before, but it's not real. It's fake. So here's what's really happening. At point A, if you were to draw your velocity vector, it would be pointing straight ahead, right? You're always moving tangent to the circular path. And so that's the way your inertia wants to take you. You always want to go in a straight line. We evidenced this when I had that video when I was going around the circle with the string and the rope, and I let go and I moved in a straight line because there's nothing pulling me to the center anymore, right? And so at point A, you're trying to go in a straight line, but the track prevents that from happening, and so it pushes the cart up, and the cart pushes you up, and you all of a sudden start feeling this force upwards when you didn't expect it. And so in our self-centered way, when you go straight and all of a sudden there's an upwards force you didn't expect, you in your self-centered way, feel like you're being pushed down, away from the center of the circle, forcing you out of the circle. That's the idea, right? Centripetal, we broke down to center seeking or center pointing. Centrifugal or centrifugal literally breaks down to center fleeing. you feel like you're being pushed down, but that doesn't make any sense, right? If the net force actually pointed down, you would accelerate down and you would leave the circle. That's not what happens, right? And that's why we have to realize the reality of the situation as opposed to what we feel. At point B, if the net force actually pointed up, well, then you would accelerate up and you would leave the circle, right? That's what this illusory centrifugal force makes you feel, like you're being forced out of the circle, but that can't be true. You have to be pulled down. So what's actually happening is, again, you try to move in a straight line, but then the floor or the seat kind of drops out from under you, and all of a sudden you didn't expect that, and so you feel like you're being lifted up out of your seat, when in reality the seat dropped out from under you, the net force has to point down. And so again, your sensation is exactly opposite to what's actually happening. Now, how do we know centrifugal force is fake? Well, we go back to our original definition of force. We define force as an interaction between two objects. And so the real way we know centrifugal force is fake is that there is no second object in this interaction. I even put interaction in quotes because there's not even an interaction. Just imagine you are riding this roller coaster, and when you get to the top of the hill, all of a sudden some object just magically appears above you, pulling you up out of your seat. That doesn't happen. It doesn't make any sense. There's nothing there pulling you up out of your seat. At point A, there's nothing there pushing you down to your seat. No matter how real it feels, there's no second object. And so this is illusion. There's nothing there. There's no actual centrifugal force pushing you out of the circle, right? Now let's go back to our pictures here of the Ferris wheel. And even though you don't go very fast in the Ferris wheel, you may not notice this difference in normal force. There is a difference in normal force. And now I want you to think back to the first time we were talking about this, again, back with those elevator problems, when we were also dealing with situations where normal force was either larger than weight or smaller than weight. And you might recall we defined a term that described this difference in sensations that you feel. Remember what that was? Yeah, that was the idea of apparent weight. And you might recall we defined apparent weight as being equal to normal force, right? Your perception of your weight, how heavy you appear to be, is completely defined by the normal force when supported from below. And so in this situation, when you're at the bottom of the valley, either in the Ferris wheel or if you're going really fast on this roller coaster, or if you're in the car and you sort of bottom out in a valley, the normal force must be larger than weight. How do you feel? You feel squished down into your seat. You feel heavier, right? Because of course normal force is larger than weight. This all agrees with what we said before. When you're going over the top of the hill, whether you're in the car going over a hill or on the roller coaster going over the hill, you feel lifted up, because what really happens is the normal force all of a sudden becomes less than your weight, but because of our self-centered way, we think everything happens to us, we experience a smaller normal force as feeling lighter or being lifted up out of your seat. And it's a very real sensation. No matter how much physics we know, it feels really real. Like, for example, I know when I've been on Nitro, you've ever been on Nitro at Six Flags, you really get a sense of this, right? When you go over that first hill, you feel like you're lifted up out of your seat. And in fact, it's such a real sensation. You know, they put some safety measures there just to make sure you're safe, right? And if you've ever ridden Nitro, you know there's that sort of yellow triangle with the handles. You hold on to that to make sure you don't come out of your seat. Now, when Nitro first opened, they didn't have that big yellow triangle. They actually just had like a bar that went across your knees. And me, being somewhat vertically challenged, when I rode it, it just barely covered my knees. And I'm like, oh, I don't know about this, right? And so the first time riding it, when I went over that first hill, I really felt like I was going to leave my seat. I mean, I knew all the physics. I knew the engineers did their calculations, and I knew it was going to be safe, but it was such a real sensation. I'm like, oh my gosh, this is it. This is the end. In my mind, I'm making up my will. I'm like, oh my gosh, I'm not going to make it here. Of course, obviously I did, and the engineers did their job, but it is such a real sensation, this idea of centrifugal force. But again, it is fake, and we know it's fake because there's no second object in the interaction. So here's a good way to remember centrifugal force is fake. Centrifugal force is the fake force you think you feel forcing you out of the circle. I know that's silly, but you know what? It might stick in your mind, and maybe it'll help you remember.